squared times this correction factor, which is capital N minus n over capital N minus 1. If the if you're drawing with replacement, then then the x size would be independent, and you just get n sigma squared. But the dependence gives us this extra correction factor, which makes the overall variance smaller. Today we're going to review the concept test from last time and talk about correlation. Finishing section 6.4. So last time we considered a Poisson lambda process. TR is a gamma R lambda, is the rth arrival time. Covariance of T1 and T3 equals. One person writes each arrival in a Poisson process is independent. Therefore, T1 and T3 are independent, which means the covariance must be 0. So this is not right, because although the Poisson process, the arrivals are independent, the time to those arrivals from time to 0 are not. So clearly T3 is the time of the third arrival, and that it must be longer than the time of the first arrival. So T3 is dependent on T1. One person writes break T3 into T1 plus W2 plus W3, where W2 is the inter-arrival time between the first and second, and W3 is the inter-arrival time between the second and third. Then W2, W3 are independent of T1 by bilinearity of covariance, and the covariance of independent variables is 0. We can simplify to variance of T1, so we get 1 over lambda squared. That sounds good. Another person writes, find the covariance of T1, T3 minus T1. Use the covariance property and the variance of T1 to find the covariance of T1, T3. Yes, that's the way I solved it. So 0 is the covariance of T1, T3 minus T1, which is the covariance of T1, T3 minus the variance of T1. And we know the variance of T1 is 1 over lambda squared. Furthermore, the covariance of T1 and T3 minus T1 is 0, since T3 minus T1 is just W2 plus W3, which is independent of T1. So yeah, and then you just solve for the covariance of T1, T3. So correlation builds on covariance. It's just the covariance divided by the SD of x and the SD of y. Those are constants, so they go into the expectation, and it's just the expectation of x star, y star, where x and y are in standard units. And you can interpret this in this picture. So imagine you have a scatter plot, and we have the expectation of x and expectation of y, and that divides up the plane into 4 quadrants. Now in the first quadrant, the product of x star, y star is positive, because x star is positive and y star is positive. X star is positive because it's to the right of expectation of x. Y star is positive because it's above the expectation of y. In the second quadrant, you get negative, positive, which is a negative. In the third quadrant, you get negative times a negative, which is a positive. And in the fourth quadrant, you get positive times a negative, which is a negative. So if your points in your scatter are mainly in the first and the third quadrant, so those will be pluses, and so the average will be plus, and you'll have a positive correlation. If it's mainly in the second and fourth, then you'll have a negative correlation. So that is sort of an intuitive idea about correlation. So let's do an example that we just talked about. Consider a Poisson process. TR is gamma R lambda. be the Rth arrival time. So we show that the covariance of T1 and T3 is 1 over lambda squared. If we wanted to find the correlation of T1 and T3, we'd need to divide that covariance by SDT1 and SDT3. So that would be 1 over lambda times square root of 3 over lambda. So that will essentially cancel out the lambdas, and you'll get 1 over square root of 3. It makes sense that this is a positive number, right? Because T1 and T3 are clearly positively associated. And notice that the covariance of T1 and T3 is 1 over lambda squared. So if lambda is really small, then the covariance could be like 10 million. But the correlation, as we'll see, the correlation has to be a number between -1 and 1. And so by dividing out by the SDs, we get rid of the lambda squared. So here's another problem. Suppose that the sum of k exchangeable random variables is a constant. Find the correlation of n1 and n2. So we take the variance of both sides. So the variance of n1 to nk, since the n's are identically distributed, is just k times the variance of n1 plus k times k minus 1. The covariance of n1 and n2 is equal to 0, because the variance of a constant is 0. And so the covariance of n1 and n2 is minus the variance of n1 over k minus 1. And then the correlation is the covariance divided by SD of n1, SD of n2. But n1 and n2 are equally distributed. So that product is just the variance of n1, and we get the covariance of n1, n2 over the variance of n1. Now the covariance of n1, n2 is just minus the variance of n1 over k minus 1. So the variance of n1 cancels out. The second question was simply an application then to find the correlation. So we did a concept test then, and so here an urn contains 90 marbles, of which there are 20 green, 25 black, and 45 red. Alice randomly picks 10 marbles without replacement, and Bob randomly picks another 10 without replacement. Let x1 be the number of green marbles that Alice has. x2 is the number of green marbles that Bob has. To find the correlation of x1 and x2, is x1 to x9 equal 20 a true identity that's useful? So yes, it's useful and it's true. So xi is the number of green of the ith person, and the xi's are hypergeometric, 10, 20, 90. To see that, just imagine laying out the 90 marbles randomly in a line, and then we can just say, let's say we wanted to know the number of green marbles in marbles number 11 to 20. So we could just pull out those marbles without looking at any of the other marbles, and the chance that there are k green marbles would be 20 choose k over 20 choose k times 70 choose k, 70 choose 10 minus k over 90 choose 10. So x2 is the hypergeometric. So they're all identically distributed, and the sum of exchangeable xi is a constant, namely 20. So we can just use the result from above to find the correlation. So the correlation, since x1 plus x2 up to x9 is 20, then the correlation is just minus 1/8. Now, if I asked you to find the covariance of x1 and x2, you could do this. The covariance is the correlation of x1, x2 times the SD of x1 times the SD of x2. Now, the SDs are the same, so this is just the correlation of x1, x2 times the variance of x1. Now, x1 is hypergeometric 10, 20, 90, and so we know its variance. And then the covariance we can figure out. Properties of correlation. So one is that correlation's invariant to change of scale, except possibly by a sign. So in other words, the correlation of xy is equal to the correlation of ax plus b, cx plus d for constants a, b, c, d, except possibly a sign. So if I just put absolute values around those correlations, they will be equal. And this is important because the correlation between Boston and New York City temperatures is the same whether the temperature is in Celsius or in Fahrenheit, which is a change of scale of Celsius. So proof of this is easy. So the correlation of ax plus b, cy plus d, we can just so that's the covariance over the SDs, and so the A and C pulls out of the covariance, and the A and C pulls out of the SD, but it pulls out as an absolute value because the SD is necessarily positive. And so then we end up with AC over absolute value of AC correlation of XY, and so AC over absolute value of AC is 1 or minus 1. So hence the correlation of x and y is the same as the correlation of x star, y star, where x star, y star are x and y in standard units, and that's because the standard deviation of x is positive and the standard deviation of y is positive. So A here is 1 over the standard deviation of x. So another important property is that the correlation lies between minus 1 and 1. So to prove this, the correlation is invariant if you convert xy to standard units, x star, y star. So let's just show the correlation of x star, y star is between minus 1 and 1. So notice that the expectation of x star is 0, the SD of x star is 1, just because x star is standard units. And furthermore, the expectation of x star squared is 1 because the variance of x star is 1, and the variance, so the expectation of x star squared is the variance of x star plus the variance of x star, what am I writing? The expectation of x star squared, and this is 0, and this is 1. And similarly for the y's. So now, if you look at x star plus y star squared, that's clearly greater than or equal to 0. You apply expectation on both sides and you FOIL. You get 1 plus 1 plus 2 expectation of x star y star is greater than or equal to 0. So you get expectation of x star y star is greater than or equal to minus 1. That's funny. This doesn't say anything. Well, I guess that's somewhat useful. Okay, so that tells us that minus 1 is less than or equal to the correlation of xy. And you can similarly do the correlation of xy is less than or equal to 1 by examining the expectation of x star minus y star squared. So here, again, this is positive. You FOIL it, but now you get minus 2x star y star. And you follow exactly in the same way, and you get the result that correlation of xy is less than or equal to 1. And this finishes the proof. Okay, guys, have a great weekend. I'll see you on Monday.